Good afternoon. My name is Weglein. Today I'm going to give a talk about predicting reference medium properties from invariances in green theorem reference wave prediction towards an onshore near surface medium and reference wave prediction. This talk will study the challenges in determining the complex near surface medium. We will discuss the criteria for finding the correct reference velocity. And we will use a marine environment as a starting point, and we will show that the invariances of the invariances of the estimated wavelet can be used as a criteria for finding the correct reference velocity. And we will study for two cases. For the data generated from a point source, the invariances is at every point below the Merriman surface. And on the other case, for the data generated by source array, the invariances can be found along one radiation angle. So this is the outline of my talk. First, I will start with the motivation of this research. And this research is motivated by the current pressing interest and challenges of multiple removal, particularly in the complex onshore and offshore blades, where you may have interfering proximal primary and multiples. And in such complex areas, inverse scattering series offers a direct way of predicting and remove the multiples and without requiring any subsurface information. And when the prerequisites of ISS are satisfied, it can deliver more effective prediction of multiples. And in the morning, Dr. May has introduced when the need for prerequisites are satisfied, how the ISS multiple algorithm reach their potentials in the marine set. And my talk will moves to the onshore problem of finding the reference medium property. And this research belongs to the three-pronged strategy proposed by M-OSRP to address the challenges of ISS internal multiple attenuator. Among the prerequisites of ISS multiple removal, the removal of reference wave is the very first step. As you see from the tutorial in the morning, that the inverse scattering series, the data D is G and G0 on the Merriman surface. And so in order to predict and remove G0, we need to understand the reference medium first. And so for the reference, when we say the reference medium, we choose the reference medium to be agree with the actual medium on and above the Merriman surface. It is required by the ISS method, and this problem is especially important because for onshore seismic application, the property of the near surface is often very hard to acquire. And in this area, there could be strong ground load generated, which can obscure the reflected seismic data. And if we have an understanding of the reference medium, we could use Green theorem to predict and remove the ground load reference wave on land, and it will be introduced in the following presentation by Jin Wu. And so by removing, predicting the reference wave, we can enhance the subsequent multiple removal steps. And the method we use here is the Green theorem. And as you have learned from the tutorial in the morning, and this surface integral on the Merriman surface can predict the reference wave when we choose the the prediction point below the Merriman surface, and it can also give the scatter wave, which is the reflected data, if we choose the prediction point above the Merriman surface. And it uses only the Merriman wave field P and the normal derivative, just by the surface integral. So, and I would like to remind you that in the last year we have shown that using the Green theorem to separate the reference wave from the reflected data, several practical issues can affect the prediction result. And one of the issues is that we have to choose the prediction point away from the cable. If we define delta z as the differences between the cable and the prediction point, as shown here, this delta z is required to be larger than at least the half of the receiver samplings in order to get a good prediction result. And this is for the prediction for PS, and also for predicting the reference wave below the surface. So next I will show the different results, different prediction results if we choose different delta z, and also for the reference wave. So this is the prediction result of the scatter wave at different depths away from the cable. And 1, 2, 3, 4 are showing the different delta z. And for the first picture, we have delta z very small, very close to the cable, and you can see that in the prediction result there are more errors in the scatter wave. That this event shouldn't be here. And if you move away from the cable, and you have a more accurate result if you predict the scatter wave at more than half of the sampling. And the same case for prediction of the reference wave. And if you predict it very close to the cable, you have more errors. And if you move away from the cable, the result is more satisfying. And the reason can be found from examining the Green function in this integral. And here I'm plotting the Green function and normal derivative with respect of the x coordinate on the Merriman surface. And different colors corresponding to different delta z, that means different distance to the cable. And the black line means very close to the we predicted that if we calculate the Green function and normal derivative very close to the cable, that the black line, you can see that it's very concentrated at one local point. This means that in the calculation of the integral, unless you have a very small sampling of delta x, this value cannot be picked up in the calculation, and this is the reason of generating the errors in the previous result. And this says that in X omega domain, it's impossible to predict either reference wave or scatter wave on the cable. But it has its advantages too, that it can accommodate non-flat Merriman surface, and for example, ocean bottom. But if you have a flat Merriman surface, you can make a Fourier transform over X. Then if you do the Green function, the Green theorem in X omega domain, you can predict it and remove the scatter wave or reference wave on the cable, which means you can isolate the wave field in the data. So to remove, predict and remove the reference wave from the data is especially important for the onshore problem. And again, coming back to the original research topic, in order to predict and remove the reference wave or ground rule, the very first step is to understand the medium of the near surface. And in this talk, we will see talking about criteria which can determine whether we have the correct reference velocity or not. And the criteria can be presence of some invariances that only the correct reference velocity will satisfy. So we will illustrate this idea of using invariances to back out the reference medium for two cases, using both the data generated from the point source or data that has a radiation pattern. And for data from a point source, I'm going to illustrate the idea from an analytical example. Again, this is the equation, the formula for Green theorem wavelet estimation. And the wavelet A omega, as you can see, it can be calculated by this integral divided by the Green function. And both the numerator and the denominator of this equation are functions of the prediction point R. But their quotients, A omega, is independent of R. This is a property that we will use, that if you have the correct reference velocity, the result is independent of R, that means invariant at different prediction points. However, if you have the wrong reference velocity, then that means you have a wrong Green function. And at that time, you will lose the property of invariance. Then the result will be depending on the prediction point R. And we will use this property to determine the reference medium of Green's function using the algorithm itself. I will illustrate the idea by from this simple 1D example. And in 1D, the surface integral becomes the value h of this term on the Merriman surface that z equals to a, and you can write Green's function and the normal derivative analytically, and the p and the dpdz can also be written out because we don't have any subsurface here. So p is just the wavelet times the Green's function, and we plug in the full terms in, and the result of p0 is just the wavelet times the Green's function. And if we divide it by Green's function, no surprise that the result is A omega, which means it is independent of the prediction point z. However, if you don't have the correct reference velocity c0, you have a wrong value of c1, then this will affect all the k in the Green's function. But it won't change the wave field G because this is the measurement. And in this case, all the k in the Green's function will change to k prime, and then you divide it by the Green's function, and the result becomes like this. This is the prediction of the wavelet. And now, if you don't have the correct reference velocity, the result is independent. It is a function of the prediction point z. This means we do not have the invariance anymore if we have a wrong reference velocity. And we will show this from the data, from the synthetic test. So the analytic test tells us that only when using the correct reference velocity, the estimate wavelet displays invariant at different points below the cable. And we use this as a criteria to find the correct reference velocity. And the steps of my test is I model the over under cable data generated from an isotropic source using analytical method. And next, I use the Green theorem pre-processing code that is provided by M-OSRP to predict the wavelet at different points below the cable, and using different reference velocities in Green's function. And I will test the case for using the correct reference velocity and giving a wrong reference velocity and a further wrong reference velocity. And this is the result of prediction of the reference rate P0. is when we use the correct reference velocity. And after dividing the Green's function, we get the wavelet at different places, at different points below the manual surface. And you can see the result is the same at different points. This is the invariant that we mentioned above. And if you use a wrong reference velocity to calculate the P0, it has some errors in the result. And then you divide the Green's function to have the wavelet. You can see there starts to change. The result starts to change at different points. That means you don't have the invariance. And if you use a further wrong reference velocity, the errors get larger, and also you have a more larger changes in different places of the wavelet results. And we put three figures together. That you can see that only when you use the correct reference velocity, you can observe the invariances at different points. Whereas if you use the wrong velocity, the result shows the variance. And with a further wrong velocity, you have a larger changes. This also indicates how can we go to the correct direction to find the correct velocity. And for the cases of data generated from the source array, the invariant is no longer at every point, but along one radiation angle that we illustrate here from a general source case. That suppose this is an extended source at rho r, and if you observe the wave field at place r, where n hat means the unit vector at this direction, then the wave field here, in the end, if we use a far field approximation, in the end, the wave field at this point can be written as the point source Green's function times this rho, which is only the function of the direction of the observation point. That means independent of r, but the function of independent of the direction. This means that if we estimate the wavelet along one angle, we can observe the invariant, and we will use this invariant as the criteria for finding the correct reference velocity. So we will estimate the wavelet along this angle. And for the test, we generated the data from a source array which consists of 7 point slots, each separated by 3 meters. And first, we will estimate the wavelet along different angles to examine the radiation pattern. And then we will estimate the wavelet along one radiation angle like I showed here. First, using the correct reference velocity, and then repeat using a wrong reference velocity so that we can examine the invariance. The first is result shows the wavelet along different angles. So this is the wavelet at the angle of 0. And if you estimate here, it changes. And so here I'm showing the angle from 0 to 85 of this source array. And you can see that the wavelet changes at different angle. It's no surprise because it's a source array. And if we estimate the wavelet along one radiation angle, and in that case 5.8 degrees, at different points, the wavelet result stays the same. So this is the 7 traces at different depths, but along one radiation angle. And all the 7 results stays the same if we calculate use the correct reference velocity. This is the invariance we just talked about. And If we use a wrong reference velocity, still estimate the wavelength at these 7 points. And so this shows the 7 traces at different, again along the same angle, but you can see there are shifts of the results. This means we no longer have the invariance if we have the wrong reference velocity. So this result shows that only having correct reference velocity can give you the invariance at 1 radius angle. And you don't have this property if you have the wrong reference velocity. And the conclusion is the question of this research is, can we find criteria that's satisfied by the correct reference velocity? And we have shown that for the point source data, the invariances of the estimated wavelength is at every point below the memory surface. And as for the data with the radiation pattern, the invariance of the wavelength is along 1 radiation angle. And for the future study, we will use the similar thinking of using invariances to study the complex onshore or ocean bottom near surface problems. And thanks for all the sponsors. Thank you for attention.